When we survey the universe on its grandest scale, it reveals a startling consistency in every direction. The cosmic microwave background, the afterglow of the Big Bang, maintains almost exactly the same temperature regardless of where you point your telescope. If, in the first trillionth of a second, the universe underwent a period of extreme, exponential expansion, then regions that are now light years apart were once close enough to interact and smooth each other out. On Earth, if you walk in a straight line long enough, you eventually return to your starting point because the surface is curved. But when we measure the universe, its geometry appears almost perfectly flat, with no detectable large-scale curvature. Einstein's equations of general relativity allow for universes of all shapes, most of which are far from flat. Somehow, our universe seems to be balanced on the knife edge of flatness. Inflation solves this by stretching out any initial curvature, much like blowing up a balloon makes its surface appear flatter locally. By blowing the universe up to such an immense size, it appears smooth and straight. Inflation also provides a natural mechanism for the seeds of galaxies. It offers a path from near uniformity to complexity, acting as a bridge between the randomness of the quantum world and the largest structures of the cosmos. Yet, for all its elegance, inflation has its critics. One reason is its reliance on a hypothetical field we've never directly observed, the inflaton field, which supposedly drove this ultra-fast expansion. This field isn't part of the standard model of particle physics, and no particle associated with it has ever been detected. To some, this feels like inventing a new form of matter just to make the equations work. Others point out that inflation models can be fine-tuned in so many ways that they can fit almost any observation, making them difficult to test or falsify. Science relies on falsifiability. If a theory can be adjusted to match any data, does it lose its scientific soul? Nevertheless, inflation has survived rigorous testing. The fine textures in the microwave background match inflationary predictions with high precision. Discoveries from the 1990s and early 2000s gave the theory a massive boost. The distribution of galaxies on the largest scales also aligns with the path drawn by inflation. These successes lead many scientists to believe that, in some form, inflation is pointing us in the right direction. In many versions, inflation doesn't end everywhere at once. It might stop in some regions, forming bubbles of space like our own universe, while continuing forever in others. This is known as eternal inflation. If true, our universe is merely one bubble in a sprawling foam of multiverses, where each bubble might possess different physical laws, different natural constants, and entirely different forms of matter and energy. Thus, a neat solution to a few cosmological puzzles suddenly opens the door to a dazzling, nearly untestable reality. The story of inflation embodies the spirit of modern cosmology. It boldly pushes our understanding back to the first moment of existence to explain why the universe looks the way it does today, linking the smallest scales of physics to the largest scales of space. It brings clarity to once unsolvable questions, but in the process, it asks deeper ones: what drove inflation, and what made it stop? Can it be tested more directly? If eternal inflation is real, what does that mean for our place in the cosmos? The hope is that a clue might emerge, perhaps in the subtle patterns of radiation or the collisions of high-energy particles, telling us if inflation is merely a temporary scaffold or a window into the deep machinery of the universe. The idea of a cyclic universe is ancient. Long before modern physics, old cultures imagined the universe as eternal, following rhythms and cycles like the seasons of the earth. Those ancient stories didn't talk about galaxies or quantum fields, but they held a similar intuition: time is not a straight line with a beginning, but an endless circle. Modern science, with its focus on evidence and equations, sometimes echoes this. If a singular beginning is troubling because it implies something from nothing, then cycles offer an alternative, an eternal universe born and dying in infinite succession. In the early 20th century, there were attempts at oscillating universe models. Scientists wondered, could the expansion we see today one day reverse? If gravity were strong enough to slow the retreat of galaxies, they might stop and begin to fall back toward each other. Over eons, the universe would contract and heat up until everything was crushed together, a big crunch followed by a new Big Bang. In this vision, the universe is like a giant lung, breathing forever. The oscillating model provides a neat rhythm. It explains why there was a hot, dense state without having to call it the first time. It even suggests that the universe could be infinite in time. But it has problems, specifically the role of entropy, the tendency for disorder to increase. If the universe expands and contracts, it doesn't return to a clean initial state. Each cycle would leave behind more disorder, more radiation, more black holes, and more broken symmetries. After infinite cycles, the universe would become too messy to sustain eternal rebirth. Later versions attempted to bypass this, suggesting that entropy might be diluted by massive volume or that the bounce itself resets the system. In recent decades, the concept of cycles has returned in the form of brane cosmology. Inspired by string theory, this model doesn't just imagine 3D space expanding and contracting, it envisions our universe as a 3D membrane, or brane, floating in a higher dimensional space. According to this, the Big Bang might be the result of two such branes colliding. Every collision produces a hot, dense state, triggering expansion, and in the higher dimensional framework, this process can happen repeatedly. Thus, our Big Bang is just one event in a sequence, not an absolute beginning. The appeal of these models lies in bypassing the singularity. The universe isn't squeezed into an impossible point, but undergoes a smooth transition between phases. They might also explain why the universe is so uniform. While inflation uses expansion to smooth things out, cyclic models suggest the universe was smoothed out over its long, repetitive history. The bounce model argues that the Big Bang wasn't a start, but an aftershock of a previous universe collapsing in on itself. This is the heart of the Big Bounce hypothesis, replacing a singular beginning with a rebounding event. The simplest analogy is a ball hitting the ground. It falls, flattens under pressure, and then springs back up. In cosmology, a universe collapsing under gravity might do something similar. Upon reaching an extreme density, instead of ending in a singularity, it releases its energy outward to begin a new expansion. From our perspective, that looks like a Big Bang. One reason the bounce model is attractive is that it avoids the problem of the beginningless start. The universe doesn't shrink into an infinitely small point, it reaches a minimum scale and turns around. However, the mechanics of a bounce are tricky. Ordinary matter under extreme gravity should collapse into a singularity. Why wouldn't a shrinking universe end in a big crunch? Some models turn to quantum mechanics. Quantum effects can sometimes provide a quantum pressure that resists collapse. Just as electrons in an atom resist being squeezed into the same state, the geometry of space itself might resist being compressed below a certain limit. Loop quantum gravity, LQG, suggests that space-time is woven from tiny, discrete loops. Because of this, space cannot shrink indefinitely. At a certain minimum scale, the compression stops and the geometry pushes back. In loop quantum cosmology, the universe reaches this minimum value and then bounces into expansion. What we call the Big Bang is actually the pivot point where contraction became expansion. If a bounce occurred, what survives from the previous world? Would any scars from the pre-universe cross over, or does the bounce erase all memory? Some theories suggest traces might survive in the distribution of matter or the patterns of gravitational waves. Others believe the bounce reshuffles everything, leaving our universe with no memory of its parent. The bounce isn't a magic key, it also faces challenges like the entropy problem, but it remains. Finally, black holes, often seen as the ultimate traps of the universe, might be something else entirely. We think of them as dead ends where light and matter are lost forever. But physicists have flipped this idea. Perhaps a black hole is not an end, but a beginning. When matter falls into a black hole, it might not vanish into a singularity, it might open up a brand new universe on the other side. This connects the crushing power of a black hole with the birth of an entire cosmos. According to general relativity, once you cross the event horizon, space and time are twisted into a new configuration. Instead of collapsing into nothingness, it might trigger the birth of a new, expanding universe, a baby universe. From the outside, we only see a black hole devouring stars, but on the inside, a new cosmos with its own space, time, and laws might be inflating outward. In this view, our own universe might have been born in the heart of a black hole in an older, parent universe. Black holes, then, are not just engines of destruction, they are the wombs of new realities. The elegance of the baby universe theory lies in how it bridges two of the greatest mysteries in science: what happens inside a black hole and where our universe came from. It ties them together into a single narrative. The violent inward collapse of matter is not a dead end but a transition, a handoff where information and energy are reborn in a different layer of reality. Of course, we cannot directly peer inside a black hole. By definition, those outside the event horizon see nothing, making this idea nearly impossible to test directly. Instead, scientists turn to indirect evidence, using simulations that combine relativity and quantum theory to study black hole behavior. These models suggest that at the center, the dreaded singularity might be smoothed out into something else. If so, the extreme conditions at the core could indeed give birth to a new region of space-time branching off from our own. Another line of inquiry asks if the structure of our universe hints at this origin. Some researchers propose that the physical laws we observe, the strength of gravity, the charge of an electron, the masses of particles, might be inherited from a parent universe. In this framework, every universe born inside a black hole has physical laws that are slightly different, much like children who resemble their parents but aren't identical. Over countless generations of universes, configurations that favor the formation of stars and black holes would become more common, because only those universes can reproduce. This is known as cosmological natural selection. The idea that the universe evolves and passes down its traits like a living organism is a breathtaking concept, though it currently lacks a definitive observational test. Critics point out that if a theory doesn't provide testable predictions, it leans more towards speculation than science. Even if universes are born in black holes, we might never interact with them. Each baby universe possesses its own space and time, eternally severed from its parent. To us, it is as if it never existed. Yet, this bold hypothesis suggests that creation and destruction are not opposites but two sides of the same coin. A star collapsing into a black hole looks like an end from our perspective, but it could simultaneously be the most dramatic beginning elsewhere. The millions of black holes in every galaxy might be the nurseries of infinite realities. If our universe was born in a black hole of an older cosmos, then the Big Bang was merely the starting point of our specific branch, while the true story extends back through a cosmic genealogy that may never end. If this is true, the question "what happened before the Big Bang" is no longer meaningless. The answer could simply be another universe happened. Imagine our universe as a giant, invisible sheet. Everything we know, galaxies, stars, planets, and the laws of physics exists on this sheet. In the language of string theory, this sheet is called a brane. String theory doesn't stop at one sheet, it allows for many branes to be stacked or drifting within a higher dimensional space. If such branes exist, our universe might be just one among many, each carrying its own version of reality. Imagine two vast, invisible canvases moving through higher dimensional space. If they collide, the energy released would be unimaginable. To us, living on one of these branes, it would look like a big bang. What we call the beginning of everything might just be the aftershock of two invisible worlds clashing. This picture arises from the mathematics of string theory, which attempts to unify all fundamental interactions but requires extra dimensions to remain consistent. In some versions, these extra dimensions allow for branes of different shapes and sizes. Our universe could be a 3D brane embedded in a higher dimensional bulk. Unlike inflation, which uses a rapid expansion to smooth out the universe, the ekpyrotic or brane collision model explains these observations through brane dynamics. If our universe was born this way, what stops it from happening again? Branes might drift and collide repeatedly over unimaginable time scales, opening the possibility of a cyclic multiverse. Big Bang-like events would happen again and again, not inside the same universe, but on a grander dimensional stage. The mathematics of tiny vibrating strings explaining why galaxies exist suggests that the smallest and largest scales are linked by invisible threads in a higher dimensional realm we cannot perceive. If a brane collision triggered our Big Bang, it might have left unusual signatures in the cosmic microwave background, subtle asymmetries or alignments that don't fit standard inflation. Thus, we view the universe as part of a larger system. Creation is not a unique miracle but a continuous process. What we see might be just a slice of a much grander reality crowded with other branes and other universes, each with its own laws, some desolate and dark, others teeming with stars and life, but shaped by different constants and forces we may never know, save for the faintest echoes of a collision. Some theories propose that the Big Bang didn't just create our universe, but also a mirror universe, one that is similar to ours in some ways but inverted in others. Unlike the bounds theory where a universe exists before us, this mirror universe was born at the same origin point but unfolded in a completely different direction. This concept stems from several physical puzzles, most notably the matter-antimatter asymmetry. According to our best theories, the Big Bang should have started with equal amounts of matter and antimatter. If so, they would have annihilated each other, leaving only light. Obviously, that didn't happen. We live in a universe of matter. So, where did the missing antimatter go? One idea is that it didn't disappear, it went to a twin universe born alongside ours, carrying away the missing half of the symmetry. This mirror universe isn't a place we can visit, it exists on the other side of a temporal mirror. In our universe, time moves forward. In the mirror universe, time relative to us runs backward. If life exists there, they would feel the flow of time as naturally as we do, though from our perspective, they are moving from our future toward our past. Nature loves symmetry, flips, rotations, and patterns that stay the same under transformation. Many fundamental laws hold true when time is reversed or when matter and antimatter are swapped. On a cosmic scale, however, these symmetries appear broken. We are in a world where time has a clear direction and matter dominates. A mirror universe provides a path to restore that balance. Our universe is the matter-dominated side, its twin is the antimatter-dominated side. Our time goes one way, theirs goes the other. Together, they complete the symmetry that nature prefers. What would such a world look like? At first glance, it might be eerily similar to ours. Stars and galaxies could form, light could travel, and gravity would carve structures. The difference lies in the ingredients. In their world, antiprotons are common, and protons are rare and dangerous. Life made of antimatter would be perfectly natural to them. If the two universes diverged at the same point, they might be forever isolated, but there might be subtle connections, echoes of that symmetrical split. The matter-antimatter asymmetry itself might be the indirect evidence. This would mean the Big Bang wasn't a single burst into a vacuum, but a split into two branches from a single origin. Some even wonder if the end of our universe is linked to the beginning of theirs, a strange symmetry where time bends into a loop connecting the two. In the 1980s, physicist Alexander Vilenkin proposed that the universe might have leaped into existence from absolute nothingness through quantum tunneling. This nothingness isn't empty space. Space itself is part of the universe, but a true void. No time, no space, no matter, no energy. To our daily intuition, this seems impossible. How can something come from nothing? But the mathematics of quantum cosmology suggests it is not only possible but perhaps even natural. The birth of the universe is a quantum event, similar in spirit to the countless quantum events happening at the subatomic level every moment. The Big Bang wasn't an explosion in space, but the tunneling of space-time itself into existence. Once it appeared, inflation took over, blowing this tiny embryo into the macro world we see today. Without quantum tunneling, the spark of inflation might never have been lit. If a universe can tunnel into being, it implies there could be countless others. Our universe is just one bubble in a sea of foam. This also suggests that the laws of physics are not eternal truths written outside the cosmos, but rules that crystallized at the moment of birth. Law and universe were born together. While we cannot create a universe in a lab, we look for signs in the cosmic structure. Even tunneling assumes some underlying framework. Perhaps the nothingness was like a pencil balanced perfectly on its tip. Eventually, it must fall, giving way to something final. The transition from a false vacuum to a true vacuum would be more than just violent. Inside the new bubble, everything would change. The speed of light might differ, atoms might no longer be stable, and chemistry as we know it might cease to exist. Yet, inside this bubble, a completely different set of physics could play out, perhaps even giving birth to another kind of universe. This mechanism is tied to quantum field theory, which suggests that particles and forces are excitations of invisible fields permeating space. These fields carry energy, and the vacuum is their lowest energy state. However, quantum fields are never truly still. A rare fluctuation could push a tiny patch of space into a more stable state, creating the seed of a true vacuum bubble. Once formed, this bubble would expand at the speed of light, rewriting everything in its path. While this sounds like the ultimate catastrophe, from another perspective, it is a form of cosmic creation, annihilation on the outside, but a Big Bang-like beginning on the inside. Some theories suggest our universe may have undergone such transitions in the past. If the vacuum changed multiple times, earlier versions of the universe might have had different laws. Each decay would be a step toward stability, leaving behind a different physical era. This is linked to the Higgs field, discovered in 2012. The Higgs boson is associated with this field, which gives mass to fundamental particles. However, measurements of its properties hint that our current vacuum might not be the absolute lowest. It might be metastable. We are balanced on a tightrope, stable enough for life to evolve, but not necessarily permanent. Don't panic, though. The timescales involved are staggering, likely trillions of years away, far longer than the current age of the universe. Yet, the possibility remains awe-inspiring. Our world's stability is not an eternal necessity, but a fragile equilibrium. Once a true vacuum bubble appears, its expansion is unstoppable because its boundary moves at the speed of light. No warning could ever precede it. One moment everything is normal, the next, the laws of physics are overturned. Some speculate this expansion is similar to inflation, meaning the bubble grows into a self-consistent universe. From the inside, it would look like a Big Bang. What if math is not just the language we use to describe the world, but the very foundation of existence? This is the mathematical universe hypothesis, championed by Max Tegmark. He argues that reality is simply a mathematical structure expressed on a macroscopic scale. Everything from the trajectory of a falling apple to the behavior of subatomic particles is described with such precision by mathematics that the world seems inseparable from it. If our universe corresponds to a specific set of equations, why should it be the only one? If logic allows for other possibilities, those possibilities might not be abstract, they might be real universes operating under their own rules. In this library of mathematical realities, there could be universes where the sum of a triangle's angles does not equal 180 degrees, where time is a complex loop rather than a line, or where space has an unimaginable number of dimensions. In this view, existence doesn't require physicality in the way we touch or see, it only requires logical consistency. If an equation is non-contradictory, it exists as a universe. Critics argue that consistency on paper does not equal physical reality. We can imagine every possible move in an infinite game of chess, but that doesn't mean all those games are being played. However, the connection between math and nature remains mysterious. Again and again, physical discoveries reveal patterns that mathematicians had already derived. Einstein's equations for curved space and the symmetries of quantum mechanics were waiting in the math long before they were found in nature. We perceive time as an arrow moving from order to disorder, entropy. But is this arrow universal? Some physicists propose that the Big Bang marked the birth of not just our universe, but a mirror universe where time flows in the opposite direction. This Janus point theory explains why our universe started in such a perfectly ordered, low-entropy state. Instead of one unlikely beginning, the Big Bang becomes a central point from which two futures diverge, one forward, one backward, restoring a grand symmetry to the cosmos. Some even suggest that traces of a previous universe might hide in our own as exotic matter, specifically strange matter. While normal matter is made of up and down quarks, high-energy environments can create strange quarks. If strange matter is as stable as some physicists predict, it might have survived the transition of a cosmic cycle, acting as a messenger from a time before our Big Bang, a fossil of a previous universe. This strange matter would be incredibly dense, heavier than any rock but not quite a black hole. Detecting it would be revolutionary. It would mean the Big Bang was not an absolute beginning and that physical laws allow for continuity across cosmic boundaries. It would be a cosmic fossil, a piece of the past hiding in the dark matter or the hearts of stars. Finally, consider the universe as a living system. If a new universe is born from the collapse or black hole of a parent, it might carry a genetic code, the fundamental constants and physical laws inherited from its mother. This is the cosmic seed bank idea. Our universe is fine-tuned for life not by a unique miracle, but because only universes with stable laws can survive long enough to be observed. Every black hole, every collapse, and every new burst of space-time is a seed thrown into the void, waiting to grow. The stars we see above us are not the result of a one-time choice, but the outcome of countless generations of universes being sculpted along paths that allow for the existence of stars, galaxies, and eventually, us. That concludes our journey through the deep mysteries of the cosmos for today. I hope these insights find a place in your thoughts and dreams. I wish you a beautiful dream and a wonderful day ahead. We'll see you in the next episode.